So, of course, well, just on the first slides, you already see our contacts. So if some of you are interested in anything that would stay unclear, or there are further discussions to go, we are always, of course, happy to receive any feedback from you, be that today or later. And so, in fact, well, we do give similar courses, of course, here at Télécom SudParis, that they are longer, which comes to model-based testing, various model-based testing strategies, in fact. And Jorge participates in these classes exactly, and he was the one who participated in the development as well of this course and the creation. And today, what we will try to do is to present maybe a very short, like very shrunk version of this to you, trying to give a little bit an overview on the subject and maybe, state certain things that were left outside for the future research of yours and of ours as well. So maybe I would go fast on the first things. It's just that I wanted to just draw your attention to the fact that when we are talking about software testing, we believe that everybody understands what it is. And certainly, participants of the software engineering school, they do understand what it is. Yet, if you start typing that on Google and you would pick some keywords that you would start using for your Google search, you might actually figure out that the notions, they are not so well established, and even for the word software, you can find different definitions, okay? And this is just because, in my opinion, this is because this is not a calculus or linear algebra that was, built a long time ago, but this is the, active area of research. And it happens that people, they do understand things differently, and they do denote things differently till nowadays, and we can go into huge discussion what's the difference between testing, verification, and validation. And I'm pretty sure that the audience, will not agree on that one immediately. So what we need to start with, at least for the nearest couple of hours, is to establish certain ground rules. Let's call them this way. So basically, to decide on our own background what we're going to call what, and we're going to use for that matter. So I guess that still the audience would agree that software testing is used exactly to assure a certain level of quality of the software under investigation, experiment, You can use these kind of words at the side. And of course, there exists, many software testing methodologies, including, security testing and others, performance testing. But we're not going to talk about them today, okay? So we'll try to focus exactly on the conformance testing. Again, it doesn't mean that I'm saying that the others, they are not useful. Yes, they are. It's just that, again, this is maybe my personal point of view is that first you would like to probably assure the conformance testing, and afterwards you would go to non-functional parts about your tool once you're sure that it's functioning correctly, actually. So in this case, we're going to assume that, and again, I draw your attention to the fact that how I, try to, which preamble I try to put in here. We're going to assume. Why am I saying we're going to assume? Because again, terminology differs. So there are people that they might assume that not necessarily testing would involve these steps that I'm going to present right now. In particular, some people, they are saying that in testing, not necessarily you should apply something. Maybe it's enough that you only observe. For today, we're going to assume that we have control points of the system and the test, and we have observation points of the system and the test, which means that in here, we're going to apply certain inputs to our system and the test, or implementation and the test, SUT or IoT, for short, and we're going to observe how it reacts. And there will be a certain context, that we're going to simulate. That can be software, another software, hardware, it can be a human, something that knows how to send these inputs and knows how to get the replies, and also maybe or maybe not can produce a conclusion, can draw a conclusion, can decide if this is correct or this is incorrect. So in this case, if we agree on the previous thing, we would say that testing indeed is a process of sending these inputs, observing these outputs, or in the proper term, output responses of the implementation of the test, and drawing the conclusion. And the conclusions exactly, we would like to focus on what? On the presence or absence of certain types of bugs. And again, I try to stay careful when picking these kind of words, because we're going to speak about specific types of bugs. Why? Because our main goal to speak would be to give certain guarantees after these conclusions they are drawn. So we want to trust these conclusions. We want to say, yes, this type of bugs, indeed, having applied this test suite, we can conclude that this type of bugs, they are not present. Maybe the others, they are. Maybe they are not. But we want to assure that this test suite at least can give you certain knowledge about certain fault coverage. So in this case, the test suite, in fact, it's a set of test cases or test sequences. We don't do much difference in that one, probably today. But there is a difference, in fact. And so this is what we're going to apply to our implementation of the test to draw these conclusions. Now, well, obviously, all of you know that this is just to know that as long as this context is not a software or hardware, in this case, we might speak about some automatic way to probably derive and execute the test cases. If this is a human, we're going to speak about a manual one. There are, of course, advantages and disadvantages, and in reality, we might say that, most probably all the test suites, in particular model-based testing strategies, they are somewhere in between, because it still involves human at different stages, but not, fully, let's say. And there are different testing assumptions, of course, that one can make. Generally, we speak about black, white, and gray boxes, which express our knowledge about the system and the test. How much do we know about it? So, we can assume that it's a black box, and that means that we know probably how the software should behave. So we have a certain specification for the functional requirements to this IoT, but we know nothing that concerns the implementation itself. We don't have the access to the code, we don't have the access to the libraries, we don't know the architecture of the software, the design of it, etc. Nothing. We just have access to the input and output interfaces of the IoT. And the rest, we just play with this particular access to be able to stimulate the system or to observe the responses of it. So in the white box, it's the opposite, right? We assume that we know everything. However, in the gray box, which is one of the most realistic scenarios, gray can be very dark gray, or gray can be very light gray, okay, depending on how much we know about the system and the test. So it's a little bit unfair, this division, but because exactly there can be different variations of this gray color. So today, most important is that we will mostly focus on the left, on the black box. Well, this we partially discussed. that you can have other testing methodologies, but we're going to go here to the functional testing. And so if we focus on functional testing, our goal is to make the fault coverage, the bigger the better, and the test length counted, for example, as the overall length of all the test sequences included in the test suite, as small as possible. So we would like to reduce the test length, reduce the efforts for the test case derivation and test suite execution, but increasing the fault coverage as much as we can. So knowing all this, I mean, these are our goals. We can, of course, discuss before moving to model-based test generation, and in particular FSM-based test generation scenarios. We can list something that most probably you all know. Various strategies how you can approach under the black box testing assumption these kind of tasks. So one of the general strategies to say, okay, I would like to use so-called equivalent petitioning, which means that I would like to split, my possible sets of inputs to my software into some classes, which would be equivalent classes, assuming that all the inputs that they belong to the same class, for them there is the same output reaction, for instance. So in this case, I will pick one, and this would be my test case. And then I will pick another from another class, etc. Now, well, there are different questions, how do you derive this petition, and who is the representative? Of course, there are other things, such as, for example, you can say, well, you know what, I'm going to just send inputs randomly, and this is also testing. Fuzz or random, well, obviously, there are also different questions that they come with along, in here is that what is the precisely the generation function, and how do I assure this randomness, and of course what this randomness guarantees. In fact, this is also an interesting point. Otherwise, there is also a known strategy, which is the boundary value analysis, when you know that, okay, I know some boundaries to the to the values of the inputs in question, and I'm going to try, those that they are close to the limits, very small or very big, for instance. No, it's pretty logical, right, when it comes to testing certain, trying to catch, bugs like overflows or something like that. And in some sense, it complements the equivalent petitioning, right? So another thing is to pre-build certain pre-post conditions, okay, in the form of if-then else, to say, okay, I would like to keep certain track of some pre and post relation, which means that if this is an input, then this should be an output. Otherwise, it should be like that. And an interesting thing is to build some kind of nested pre-post conditions. In this case, well, you can express more aspects that they probably are included into specification. So this is for the black box. For the white box, no, there are also lots of known strategies, of course, and most of them, they would rely on some code coverage. Because, of course, if you have the code, you play with the code, right? So you're saying, okay, I want to cover each loop, I don't know, at least 10 times. How much is N? For you to decide, depends on your resources, and things like that. Or, I would like to enter each condition, or I would like to enter each condition at least 10 times, etc. So I would like to inspect the branches of the code. I would like that each branch be executed at least once, or I don't know, like 10 times or something like that. Hoping that this would, in this case, in fact, code coverage, it's a nice criterion, yes. But it's not the same as fault coverage, which we're going to focus on today. So we will start with a running example. In fact, yeah, this example was picked. It's not ours, you know. In fact, it's an existing protocol. Yes, you can type and you will find something in wiki as a small spec. Yet, for this particular case, to demonstrate certain software testing capabilities and particular model-based testing capabilities, this example was picked from the works of the people that I'm going to cite. You probably know them. This is Khaled Al-Faqih, Professor Khaled Al-Faqih from American University of Sharjah, Professor Nina Yevtushenko from SudParis and HSE. And so, as we're citing them, we're going to keep their specification, but we're going to play with the implementation the way that we want. Basically, guys, if you have any questions, you can also interrupt us. Jorge, it works for you as well, right? On the way, I think you can ask the questions if you want. No questions so far. Or maybe I should also go see the chat. Well, the point is that in case you have a question, don't hesitate just to interrupt directly, okay? Or you have a comment. Because sometimes I do not follow the chat and the raised hands and stuff like that. So say we're talking about this random example that looks as follows. In fact, it's so-called password authentication protocol. That the story is as follows, you know. In fact, you have two communicating entities, right? And one, assuming, would verify the identity of the other based on, you know, the credentials of the latter, and if this is correct, if the credentials they are okayish, they appear in the database of the former. In this case, yeah, some access, some confirmation will be sent, and some access to certain, you know, resources will be given. Say, I don't know, for instance, a client is requesting certain access to certain database from a server, you know, and so the server would verify that this client is exactly this login and password. They do appear in the corresponding database of the server, and then you know that the access will be given. Otherwise, it will be rejected. So what is in here? It's a kind of a pseudocode. Yeah, indeed, it's a pseudocode because, you know, in here it's like S belongs to a certain set of possibly allowed users. Okay, so in fact, assume that the client doesn't have infinite amount of time to try to log in. Basically, assume that at max, it's like when we type our PIN, I don't know, on the ATM, it would be 3 times. So for example, same in here. So we would assume that what's going on the server side is that the server side first would receive a string, right, S, and then there will be a check. If this string, assume for the sake of simplicity that the string contains both the login and the password, right? So the server would verify, but indeed this login and this password, they appear in the corresponding set of my, you know, allowed users. If yes, then please return 1, which means, you know, give access to certain data or something like that, or certain resources. But before that, also confirm to the client that yes, your access is given, which means ACK. And you do exactly the same the second time, and you do exactly the same the third time. And if none of the returns in here, 1, 2, 3, happen to actually be executed, sorry, in this case, we would send NACK, which means no, not acknowledged, and we would return 0, right? So we can assume how it would be tested, okay, with what we discussed. And we would assume a little bit more that during the implementation, there has been a fault. In particular, It wasn't here, okay? The one which is underlined in red. Instead of returning 1, the developer returns 0. In spite of the fact that, yes, the confirmation acknowledged has been sent to the client, yet the access has not been given, okay? So we need to catch this fault. We need to find such test cases that they would actually allow us to detect this particular misbehavior. Now, well, how can we approach this? If we were in the black box, we would say, okay, some boundary value analysis can give us an idea of trying the sequences precisely of length 3, because maximum is 3 tries. Otherwise, if we were in a white box, we would say, okay, well, we need just to apply condition testing to make sure that each of the conditions is actually executed. And the last one in particular would be, and this is how we would see what happened. However, how do we do if we assume that we don't do white, that we only have the specification? And so what we invite you to do in here, basically is to introduce certain formal methods and make sure that these formal methods, they would allow you to provide certain guarantees. Because of course, without a formal model that specifies well the expected behavior of the system and the test, we could try again, some random approach. But again, we cannot be sure about the fault coverage. But if we want to be sure about it, in this case, we need something. And in this case, this formal description of the behavior, of the expected behavior of the system of the test, in fact, would be the one that would allow us to provide the test suits in the end to be executed further. So in this case, this is the general schema, right? So we start with the set of software requirements, and we assume that developers, they started here as well, and they go to produce an IoT. However, us, we work as intelligent testers. So what we're going to do is that we assume that we don't have, access to this code again, or we are in the black box, but we can play with it, which means that we can send and observe. So we're gonna, before jumping to test cases, we're gonna pass through an intermediate thing, which will be exactly a formal model that would allow us to, on top of that, automatically generate these particular test cases first to be executed in here. And then the observation of the output responses and the comparison of the expected ones versus produced ones would allow us to draw the conclusions about how good is the IoT. There would be, of course, a normal question when speaking about the fault coverage. How do you estimate the fault coverage? One of the definitions of the estimation of the fault coverage relies on the notion of a mutant, which means that in this case, of course, it is important to know that mutants, they can be for the models as well as for the code. So if we're talking about the code and code-related mutants, in this case, we can speak about some kind of a golden implementation, which allows us to later on produce certain mutants by inserting or injecting certain faults in this implementation, by changing certain operations, by deleting instructions and stuff like that. And then, given a test suite, we can execute it against this set of mutants to see which mutants are so-called killed and which ones they survived. So the more they're killed, the higher is the fault coverage. And of course, there will be a discussion. And probably you are aware that there is a huge, in software testing, there is a big, enormous community of people that they work on mutation testing in particular. And mutation testing is indeed a huge area of research. And they get interested in many questions that they are completely valid, such as, for instance, what if you built a mutant and it got to be equivalent? how do you detect them? You should actually take them away when you're calculating the percentage to know what's your fault coverage, right? And things like that. We'll not go into these details today. It's just that I would like to mention that there is a lot of research going on this, and you can find many publications that they are related exactly to this subject. At the same time, another interesting question when it comes to mutation testing is that if we are talking about the model-based testing scenario, in this case, we are not only interested in the mutants that they are representing the certain modifications of the code of the implementation itself, but also of the formal model that represents the expected behavior of the system and the test. So not only you can mutate the left ones, but you can also mutate the right ones. And in this case, you know, what would it correspond to? If it's a graph-like model, in this case, you might assume that, you know, your implementation makes you delete a certain edge or creating an edge which was not there. Or for instance, there was an edge from one node to another, but the mutant would correspond to a redirection of this edge to another node, for example. And then there is another, actually I do not know between equivalent mutants and this other question, which one, you know, is actually receives more attention currently in mutation testing, because the other question that I wanted to mention is exactly the correspondence between the code mutants and the model mutants for different languages, as well as for different formalisms that they are used to describe the system behavior. So this is not a story, and there are also many publications that they are regarding this, you know, which we will not stop today. We will dive in directly into some parts of model-based strategies, and in particular those that they are built in a very particular formalism, which is a finite state machine. And in fact, yesterday there was a talk of Alexei on abstract state machines. And one of the questions was exactly, you know, what is the difference between ASM and FSM? And it's true that ASM got to be very compact. It can be very compact, but it represents a lot of things inside, right? That you have these abstract states, and then you have predicates and things like that. FSM that we're going to talk about today, it's so much simpler, okay? Which exactly, if you refer again to the talk of Alexei and his last remark, he was like, you know, the problem is that you can build an FSM, but you will probably get a state explosion or something like that. True, completely. And which means that when we are building an FSM, we need to take care of its size. It's true. As well as about many other properties. But there is one good thing about FSMs. And I don't know if you also heard my question yesterday. It was, I personally, I tried also to look up a little bit. When it comes to ACMs, for example, they are incredible for modeling and for the verification purposes as well and things like that. But when it comes to test generation strategies, I do not know the results about the guaranteed fault coverage for that particular model. But for this model, which is much simpler, which is an FSM, there are works, and they date starting from the 70s. Okay, and I would be proud to say that they start with a very known work of Vasilevsky, which later on was adapted by Shaw, and this date back to 70s of the previous century. Okay. So, a question to you. Yeah, well, now it comes the story that, you know, I wanted to interact a little bit. So who knows then what is a finite state machine and which kinds are there of these machines? No reply. Because I'm trying to, wait, how do I do? I don't see, at the same time, I can't see my chat. This is a little bit, oh no, I can. I see participants, okay, well, I do not know why. Oh, I see the chat. Okay, nobody's typing in the chat, this is good, or bad. So, in this case, I will start presenting the model itself, assuming that you don't have much background on it, okay? So, basically, yes, state machine speaks by itself, which means that you would have states, okay, and you would have transitions. And once again, it's a great thing because, you know, Alexei already presented so much more complex formalism that now what I have to do is that I have to tell you that in here, you only have simple states, nothing inside, you know. There is no concurrency, there is no composite, there is no parallelism or something like that in this very model. Can be worse. But in this one, in the finite state machine, traditional classical finite state machine, you have a set of states, you have a set of inputs, you have a set of outputs. And in fact, what happens is that, and all of this is finite, you know, this is also a good thing. Yet there exist others, you know, when you consider countable and stuff like that, but we're not going to touch this. And so there is also a transition function, right, that contains exactly, you know, certain transitions that they are allowed in this very machine. And so a transition, what it is, a transition is like a four tuple, you know, which is a current state, an input, an output, and the next state. Which means that in fact, what's going on is that this box, you know, this FSM, stays in some internal state, okay? And inputs, they are applied in here, and outputs, they are produced in here. So it functions exactly like that. When an input is applied, it probably changes its state, or not, it can stay in the same one. And then it produces immediately an output, okay? From the external point of view, we only see these inputs and these outputs, okay? So, like, for example, this machine being in state one, when an input I is applied, it can do either way, right? It's not deterministic. It can either stay at state one, producing a one, or it can move to state two, producing the output O2, okay? And this reflects a lot the notion of a certain black box, because this internal thing, it affects in reality the behavior, which means that the output can be different, but what's inside this box, we do not know. And this reflects a lot, you know, I mean, the behavior of many reactive systems. So being at some state, they would accept some input, they would move to another state, but you know, this reactivity is not observable by us in the sense that we don't know what's inside. But what stays observable is the output reaction. And so there can be different kinds of machines, you know, of the classical finite state machines. You know, you can speak about complete behavior or partial behavior. So you will speak about complete or partial, completely specified or partially specified machines. In fact, we will probably focus today on the complete ones, because partiality brings much more complexity, in particular in test generation strategies. You can also speak about deterministic or non-deterministic behavior. We just checked an example which was non-deterministic, but if this machine, you know, which is here downstairs, is the one that you take into consideration, in this case it will be complete and deterministic, right? Because, you know, I deleted this transition, which was a loop at state one, for example. So finally, non-deterministic behavior can be also observable or not, in the sense that input-output pair will let you know, if you know a current state, what would be the next one. Of course, the most complicated case is to have partial, non-deterministic, non-observable, if I speak about these three. That's why today we will not do this. We will speak about complete deterministic. which of course is observable by definition. And so we will come back to our example. That will be the running example also during the exercises given by Jorge. It's one of the possible specifications for this particular part of the authentication protocol. Once again, this specification wasn't built by us, and I have certain critics to this very specification. But you remember there was an arrow from the set of the requirements to a formal model. And this arrow, it's a very, important arrow. It reflects a certain level of creativity. Building specifications, it's another story, right? You should stay creative, and you should also stay kind of adequate and fair to yourselves. You need to say, okay, this aspect, they're not so important, so I'm going to cut this behavior. These best aspects are very important. This is what I'm going to include. This is non-deterministic. I don't know how to deal with it. I'm going to cut it. This is very partial. I don't want to work with partial. I'm going to make it complete and stuff like that. So this machine, in fact, has two inputs, which are called RAR plus and RAR minus, according, which is good and bad credentials, and the sign, which they refer to acknowledged and not acknowledged as the possible output replies. Okay, because this is true, a string comes, the reply is produced. Stays pretty binary, actually. As for the states, the authors, they propose to start at the initial state, assuming that the machine is initialized. And when it comes, the good pair, of login and password, a confirmation ARC should be produced and the access should be given. So the machine would move to state open. Otherwise, if it comes the bad one, sun should be produced and another attempt should be given to the user. So in this case, we move to the state try to, meaning that you can try again. Same story happens in try to, if again it's bad. You can already bring some critics to this specification, but what happens if there is good? And this behavior is not specified. And the same exactly behavior you can observe at state try 3. When there is the third time, the wrong pair, then it moves you to state close. Okay, so what do I do with it? Suppose that now that I have a spec, I can think how to test my implementation. So we're going to use this spec precisely. It's the same exact schema, but in reality, it is to say that there can be different formal models, okay, that they can be placed in here. And we're going to speak about those. They are FSM-based test generation strategies, which means that in here, it's a finite state machine. And we're going to focus on how this FSM can help to build a test suite. And we're going to focus on how good is this test suite, i.e. what's this fault coverage is. We're going to, in this case, assume that if the spec is the finite state machine, we will return now to a notion of a mutant, assuming that what could happen with this golden finite state machine, the correct one, that during the implementation, how can it get mutated? Well, there can be only two types of faults that they can happen, namely transition or output faults. Either the transition got redirected, for example, which means that the next stage, state has been wrongly assigned, or there was a wrong output. Okay, and as long as we agreed on this, the first test generation strategy that we might imagine would be a transition tour. This is the one which is widely used everywhere because it's simple and because it still brings experimentally shown that it brings very high fault coverage against many different code-related mutants. Okay. What do you think is a transition tour? and how it works and what would be the fault coverage. Any ideas? I need to return to the chat. Well, guys, you can just speak up, or you can type it. Yeah, I'm trying to follow. Yeah. So far, no ideas. No, well, I will try to hit you on the first one, but I still expect the reply on the second. So the transition to speaks by itself or for itself, you know. In fact, it means to traverse each transition at least once, which means that if we return to our previous example, you know, here, if I want to build a transition tool, I want to build such a test suite, you know, that at least each transition here is covered. Okay. Now, for example, you know, I mean, here you don't have much choice, you know, so you have to include this RAR plus, and then of course you can include RAR minus, or you can include, you know, directly one single test sequence that covers these three transitions, you know, from act to try 2 to try 3 to close accordingly. So it will be minus, minus, minus. Okay, so this is the story of how the test suite is derived. Okay, we are not speaking about the minimality of it. We are not speaking about sometimes, you know, you can build a transition too if you're lucky. That probably is represented by a single sequence, right? So it only contains one single check-in sequence. Sometimes it is not possible, just like in our example, and you need to reset your system, you know, bring it to the initial state and then send another test sequence. So given this, you tell me, please, what is the fault coverage in this case, in your opinion, of this test generation strategy? And of course, I draw your attention to the fact that we are interested in the guaranteed fault coverage again, right? So we want to say all the faults of this type will be detected. Full, when you are saying full, yeah, I see, guys, you are typing in the chat, so it's fine. If I miss you, also let me know. So Nikolai says that it might be full, which means I assume that what you're trying to say is that this test generation strategy will detect both transition and output faults. No, well, basically we have, it's very simple, because we have, you know, some possibilities to reply. As we know that there can be only two types of faults, right? Transition and output. So you have possibilities. Possibility number one, let's say full, i.e. I'm trying to type in parallel, i.e. output plus transition. All possible changes to the FSM. Yeah, but exactly, we can only do two types of changes, right? We agreed. Once it's an FSM, we can only do two types of changes. Either it's an output, which is different, or it's a transition that got to be redirected to a wrong state. So in this case, it can be either output plus transition, or I say output only, transition only, and option 4, none. Nor output, no transition. Okay? So you agree that you can only have these 4 choices. As long as you assume that these types of faults, they are the only ones that they can happen while implementing, which is in reality exactly the case if you start by modeling your behaviors in FSM. I mean, not your behavior, but the behavior of the system and the test and of your interest. So I see that there are 2 persons that they believe that this is 1. Who else believes that this is 1? Or just type the number, you know, but we'll try to vote. Let's try to vote for the correct reply. I'm trying to motivate your people. Okay, more ones. Somebody believes that this is 2, maybe. Another one. Somebody believes that this is 3, maybe. Or maybe 4. Maybe if we have new sequence of output. I'm not quite sure I understand the comment, but yeah, we are allowed to have different sequences, right? We are allowed, not necessarily we need to apply just one. And each time we are allowed to observe the output, of course, reaction to conclude. Aha. Okay, so the majority is still for 1, but there is Nikolai who now believes that this is 3, which means transition only. Would there be anybody who believes that this is 2 or this is 4? Okay, there is 2. Still 1 is winning. I think so. Yeah, there are 3 persons that they vote for 1. I excluded Nikolai already. Then there is 1 person voting for 3, 1 person voting for 2. Anybody else would like to express their votes? Well, it's pretty funny. This definitely has coverage on transitions, but I doubt it can cover all the output variations. That's a very good point that you are saying, Nikolai. But I cannot agree with that. And I will show you why, in fact. It's a little bit tricky, actually. But in reality, let me put you somewhere at the side. What happens is that this is the correct reply. The correct reply is 2. And of course, you would wonder why. And we would just get back to the previous example and you will see it simply, okay, you can formally prove it, but it's not so difficult to do so. So if you get back to the previous example and you would assume that your test it contains 2 sequences, okay? Let's assume that for the sake of simplicity, we would write each sequence from a new line. So the first one is rho plus, the other one is minus, minus, minus. So expected output responses would be sa and san, 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 right? So we cover this transition and then we cover this sequence of transitions. And so assuming that there had to be an output fault during the implementation. So for instance, it was from the transition that connects try 2 to try 3, okay? So in fact, that happened, you remember, in here it should have been san, but in fact, during the implementation, we placed sa, okay? If this is the case, then you can see that this fault is detected. How you can see it? But because to this task suite, the expected output reaction is sa, san, 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 but the observed one would be, when you apply to this implementation, you would see sa, and then you would see san, sa, san, which the second one is so totally different from this one. So the fault is detected because the observed output reaction is not as it was expected. Now, assume that this happened and it was a transition fault. So it got redirected wrongly. It does cover transitions, but not always it allows us to detect it. Because in here, if the first one just got redirected wrongly, and we never had a prolongation of the sequence, you see, we never had to apply anything afterwards, after our plus. If instead of open, it happened to go to close, we will never observe it. Because the expected output reactions and the observed ones, they actually coincide. That's why a transition tour does not detect a transition fault. Not always. In fact, it is known experimentally that a good transition tour, a long one, for a dense machine, let's say, it would detect also lots of transition faults, but not all of them. This is not a guarantee, okay? This is the most important, and what we are searching is the guarantee. So, but as for the output faults, there is a guarantee, okay? Because each transition is covered, and exactly we apply each input and we observe if the output is correct. But we don't know if the next state was correct because we don't see it, because it's in the box, because it's blank. And of course, there is a next question that comes. I mean, what do we do? Because we still want to detect transition faults, right? And that's why I will tell you, because the transition tour detects all output faults in almost all, no, I actually, maybe it's a strong statement, but I will still say in all test generation strategies, there is a part which relates to traverse and transitions, because you still want to reassure yourself about potential output faults. But if you want to reassure yourself about the transition faults, then you should not stop here. Then, when you reach this close, you would like to apply something more to make sure, did I reach open or actually I reached something else, which in particular case is close? Which means that you need to do something which comes to distinguishing the reached state from all other candidates. Distinguishing means to apply something, which exactly is called distinguishing sequence, such that the observation of the output response will allow you to uniquely conclude, I know it is open, or no, it's not open, it can be try to or close or anything else. And so that is why when testing against finite state machines, almost all test generation strategies would rely on two steps: to traverse, to reach, to traverse, and to distinguish, to know what did we reach in reality, what did implementation reach, because we cannot see what it reached. And there are many methods, okay? But these methods that they are listed in the slide, they are this way or the other, they actually represent some modifications and improvements, in fact, of the original one, which is they refer to as W method, which is Vasilevsky method, okay? And if we want to stay formal enough to speak about the fault coverage and things like that, no, we need to introduce another formal notation, which in particular is referred to as fault model. Fault model is a triple, where you have a specification, how the system should behave, the conformance relation, which means it's kind of giving you an oracle or something to say, I compared the observed reactions to the expected ones, and I know if it conforms or it does not. In our case, we checked it was just the equivalence. They should coincide the reactions, but it's not necessarily the case, right? If you have non-deterministic choices, for example, in your specification, maybe you would like to check an inclusion, or which is referred to also as reduction, which means that you are saying, I want to reassure that my specification, it allows this, and the implementation does only what the specification allows, but doesn't do anything else. So there are many conformance relations introduced for different specifications, okay? Different state-based specifications. So for today, we will only be interested in equivalence when the specification is a finite state machine, okay? And so what is a fault domain? Fault domain, it's enumerated or listed somehow possible fault implementations. And such as, for instance, we can introduce all the mutants that they contain all output faults, okay? And we want to say that we build such a test suite that it is exhaustive with respect to this fault model. So exhaustiveness means that we would like to reassure that whenever there is such an implementation in FD in the fault domain that is not conforming with respect to the set symbol to our S, in this case, we would like to detect it. So the test suite is capable of detecting it. So we want to return the verdict fail for such an implementation. And as we said in testing methodologies, in model-based testing, the notions are also adopted, okay, over gray, black, and white boxes, depending on how these mutants they are given in here, okay? So if they are given explicitly, one by one, in this case, we speak about the white box, because we assume that we know the structure of the mutant as well as the structure of the specification itself. If we list them through a big non-deterministic, potentially huge machine, such that sub-machine can be a mutant, in this case, we speak about a gray box testing. And finally, the one that is of our interest today is the black box again. In this case, it has been proven that if we say, I know nothing about my implementation, I cannot guarantee anything. But if I know the maximum number of states of this implementation, this is enough to provide guarantees. So black box means that I know how many states can the implementation have, which because we're gonna do the distinguishability, we need to know to distinguish from what and how many times. So we spoke already about the notion of the distinguishability. Now what is left is to formally define it. So assume that you have certain states in your machine. Can be a pair, can be a subset, can be all set of states of your machine. You would like to build such a sequence, alpha, which we'll refer to as DS, distinguishing sequence, such that after applying alpha and observing beta, be that 1, 2, 3, m, you would immediately know what was the initial state. This is exactly what you should do, right? You want to apply something that you would know, was it open or was it closed that are reached. So in case of deterministic behavior, this is just non-equality, which goes here. When it is non-deterministic behavior, this is a little bit more complicated. You will check that they don't intersect, the possible output reactions and things like that. I need to tell you that, yes, good news, there are methods, many, how to guarantee the detection under the black box testing assumption of both output and transition faults. Bad news is that they are very demanding with respect to the type of the specification, and they're complex enough when it comes to the test lengths. Okay, so these are already, the whole slide is devoted to the restrictions. We want our machine, we spoke about many of them already, to be deterministic, complete. Also, it should be connected and reduced. Connected in this sense, it means initially connected, which means that I can reach any state from the initial one. Okay, so I don't have like separate paths in my diagram, transition diagram, which is logical, because if I can't reach some state, you know, how do I want to traverse certain transitions from this state? New notion is the notion of reduced or so-called minimality of the machine, which means that I want to make sure that each state pair is distinguishable in reality, which means that I want to know if I can distinguish open from close, then this is the thing that I'm going to apply after potentially reaching open or close. If this is not the case, of course, I will not be able to do so. And there are some constraints when you can obtain the polynomial length of the test suite. It's only when the number of maximum number of states of the implementation does not exceed that one of specification. Otherwise, it grows exponentially. So I'm telling you, this slide speaks pretty much how pretentious are FSM-based test generation strategies with the guaranteed fault coverage. You know, yes, good news, we can achieve it. Bad news is, of course, lots of restrictions and the complexity. That's why if this is one of the topics of your interest, I will tell you that what the researchers are writing now. This is very growing a lot. There is a big community that works exactly on FSM-based testing, and what do people do exactly? They are trying to reduce the complexity. They are trying to somehow, reduce the test lengths. Find certain classes when this first complexity scenario, would not be reachable. They are trying to take away these restrictions to say, what if the machine is non-deterministic? What if the machine is partial? What if it's non-observable? And things. What if it's not minimal? What can I do to it? No. So, well, not minimal, it's simple. You need to do it minimal. With the rest, it's a little bit more complicated. But you can also say that if it's non-deterministic, you just need to make it deterministic, and that's it. That's why there is a lot of ongoing research in this particular field. Okay. So if we place all these restrictions on spot, what we're going to do is that we're going to observe that this model, which is the running example, did not possess the necessary properties, obviously. So we're going to augment it. For example, we're going to make it complete. And we're going to make it complete in a natural way, for instance. We're going to say, but in try 2, there was no transition under our class. So we're going to add it naturally to state open, okay, with a positive reply, acknowledged. And when we're going to do the same, for instance, at try 3. And we're going to do a similar thing at state close, but we're going to return the reply no. Okay. Because you already used your 3 tries, you cannot do it any longer. Now it is complete. Now it is deterministic. The question is that, is this reduced? So is it true that each state pair of this machine is actually distinguishable? Question to you. Well, the reply can be a little bit long, right? Because as usual, if you oppose, you just need to give, it's enough to give just one single counter example. But if you agree, as you do not know anything about the minimality, but its definition, you can only prove it by definition. That's it. So either you are saying, no, it's not reduced. And in this case, I'm asking you, which state pair is not distinguishable? And you are telling me, for instance, I don't know, arc and open are not distinguishable. Or I don't know, open and close, let's say, that they were not distinguishable before. Even in the new model, augmented one, they're still not distinguishable. And it's okay if you manage to persuade me. Otherwise, you are telling me, no, it is reduced, or yes, it is reduced, depends how you see it. And in this case, you need to, for each state pair, give me, a distinguishing sequence. Because that's the only thing that you know, right, the definition. No, well, let's start together, right? I'm going to type in the chat. So for instance, we will pick a pair. Exactly, we will start with open and close. Is there any guess? Would there be? In fact, yes, right? This alpha, it would only contain one single input, which is R plus. Why? Because the output reaction at state open would be SR, and the output reaction state close would be SUN, which they differ, which means that these two, they get to be distinguished by one single input, right? Now, not always we are lucky that this is one single input that distinguishes a pair, right? Sometimes you need to do longer sequences, right? Much longer. But there is a property that, you know, in a complete deterministic, if you can distinguish, you would distinguish with the length at most n-1 for a pair, where n is the number of states. So not that long for this very type of machines. So let's pick another pair. I don't know, say we pick close and try 3, I don't know. So the question is the same. Is there an alpha that distinguishes? And if so, does anybody see this alpha? Yeah, the problem is that if you apply plus, oh, you're good. Yeah, it's true. Plus, rare plus, it works. It's true. Because, yeah, because at try 3, we would observe, I'm trying to type in parallel, at try 3, we would observe sa, while at close, we would observe sun. Works. So these two pairs, we already checked, they're distinguished. Let's pick, I don't know, try 2 and close. Is there an alpha? No, what if we try, for instance, something like, yeah, if you apply R plus directly, right? This is a hypothesis. What happens is that at state try to yeah, at state try to, you would see which ones are we distinguishing? No, it's okay. Yeah, at state try 2, you would see sa. It's good. And at state close, you will see sun. Now, if you want to distinguish, for instance, try 2 and try 3, that might be a little bit more interesting, I guess. Yeah, this one. Which one? Is there any? Plus is the option. Let's see, if you apply plus plus at state try 2, you would see sa, you agree? And if you apply at state try 3, you would see sa. Wouldn't work. They are the same. They should be different. Yeah, but it's a very good idea, actually. Continue in this flow. Yeah, that's a perfect one. So if you apply minus plus, you see try 2 would give you sun sa, and the try 3 would give you sun. So you see, you could not stop at just minus because they would be the same, the output reactions. But then you apply minus and you keep them the same, and then you prolong them just a little bit, and it's enough to actually distinguish. Okay? And you can continue. Okay, you can play with this. Like for instance, I don't know. Let's do ACK and try 3. Anybody has an alpha? Let's see if I apply it ACK minus plus. What happens is that I see sun, sa, right? And if I apply try 3, I see sun, sun, true. Okay, so the point is that, you know, we tried quite many, but maybe not all of them, but I will tell you that the reply is yes, okay? And in fact, for all state pairs, you should have like 10 of them, I assume, because we have 5, right, states. Yeah, well, for instance, ACK and open, they are alone, okay? You need to see that, for instance, you need to apply this loan to distinguish. Let's see if this is true, that ACK and open, they get to be distinguished by this thing. So if I apply in ACK 3 minus is 1 plus, what do I see? I see sun, 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 4 times sun, okay? And if I do it in open, I see 3 times sun and 1 times sa. Exactly, they get to be distinguished like that. And I can't do it shorter, right? Because I need to push, you know, this transition from ACK to close to be able to distinguish with the final output R plus between open and close. This is the strategy. But there are, of course, more efficient techniques how to build these distinguishing sequences, okay? The most important thing is that if you collect all these distinguishing sequences for state pairs into the same set, you might call it distinguishability set or characterization set. And this is how the W method it works. In fact, you need to, just what we started from, we said you need to reach, you need to traverse, and you need to distinguish. So the reachability set, or so-called state cover set, also need to be derived. And so this picture I picked also, you know, from the slides of the colleagues mentioned before. So in fact, you, starting from the initial state, you are reaching a state and you do 2 steps. Either you traverse a transition and you hang here, append the W set, or you append it directly. Because whatever you reach, you would like to distinguish, you would like to reassure yourself that you reached the correct one, okay? And if you do it this way, well, in this case, well, formally it looks like that. It's a union of TS1 and TS2, written this way. Any sequence of V appended to any sequence of W, any sequence of V appended to one input appended with any sequence of W. This is in fact the general idea of Vasilevsky to build and show, to build the test suite. And of course, there are different possibilities how to, because this is where we started with you, right? We said that it's currently everybody's trying to see how to reduce these test lengths, you know, how to make it simple and stuff. So one of the possibilities is to say, but I don't want to attach the whole W. It's big, you know, like in here we have not 10 sequences, but I don't know, 7 or 6, because some they get to be repeated. But I would like just one if possible. In this case, I would be interested in building one single sequence that distinguishes all set of states, okay? Just like in here we were saying, right? When we were given the notion of a distinguishing sequence, we were saying it can be a pair of states or it can be all the set of states. So if I manage to build one sequence that distinguishes all sets of states, it automatically means that it distinguishes each pair. So instead of hanging in here the W, I will hang just one single sequence, which is the DS. So, no, well, for that, you need to, of course, know how to build such a sequence and how to check if it exists, because it doesn't always exist. It's bad news again, you know, existence check is space complete, this task. So another thing, typical complexity issues that we have to deal with when talking about FSM-based testing, but still it's doable, good news, okay? And you might, of course, understand that if it is space complete, it means that, you know, it cannot be a polynomial over length, okay, for the sequence. So if you want to derive it formally, you can rely on a notion of so-called truncated success tree that represents somehow an unrolled behavior of the machine that in fact represents your specification. So we can say that for a given subset of states, we're gonna try to see if I apply a corresponding input, which I label my edge with, what happens to the possible next states? And I would say that I will split the current subset of states into smaller subsets with respect to the output that they produce. So I will say, these are the ones that they produce the outputs are, and these are the ones that they produce the outputs on. Can be more subsets if more outputs in the machine. Good news if it's deterministic, there is always a partition. Bad news if it's not deterministic, then there is a cover, okay? And because they can overlap. And still you can do it. I mean, there exist methods, okay, to do so. But the constraints on the lens are still there, okay? Yet if you manage to build such a sequence, it is possible that, well, certainly your test suite will, you know, the tree will, you know, gain in width, right? Will it gain in depth? This is to see, because maybe not, because, you know, the length for your specification machine, even if there is a distinguished sequence, it can be really big if the machine is bad in this particular notion of badness, you know. There are other modifications of the W methods, okay? Almost all of them, because, you know, you cannot cut much in the reachability set, you know, in any case you need to reach a state. But you can cut in the red part and the W part. For instance, you can hang one single sequence, which is DS, or instead you can try to build a sequence which distinguishes not all the states. It can be a set still, but not for all the state pairs, but only for this very targeted state. So you can, for instance, try to build such a sequence that distinguishes the rich one from all others. UIO, of course, exists so-called unique input-output sequence for a given state. It exists more often than the distinguishing sequence for the whole machine. But it has been proven that for some particular examples, there cannot be a full fault coverage for this particular method. HSI is another so-called harmonized state identifiers, does a similar thing, but improves the OIO in the sense that it preserves the fault coverage. So in here you say, you will append the sets again, not one single sequence. The sets to reassure that there is such a sequence that distinguishes from all the current state. And there are specific conditions when the full fault coverage is actually achieved. There is a very nice paper, you know, that I try to cite exactly in here, that presents, a survey on general FSM-based test generation strategies. And this is a survey which is augmented with experimental evaluation. And then there are different machines. You can find random machines, but also you can find machines that they model the behavior of certain telecommunication protocols. And so you can see what happens to the lens and what happens to, well, there are different experimental patterns, you know, that they are in this particular paper when it comes to the complexity and the lens and the time needed to generate and stuff. So you can see that, for instance, you know, in here, UIO performs well, right? And certainly W is the one which is the worst, right? Which is above everything, you know. There are other modifications such as WP when partial machines are considered and things like that. So in case you're interested, throw a look, okay? Not only you will find a good presentation of the methods, but also it will give you an idea how they perform, okay? As from my side, I would like just probably to mention that there are other possibilities to reduce the test length, okay? No, for example, you can say, I know about the DS in particular, that this is possible, and people, they know it since the paper of 94 from Lee and Dinakakis, when in fact you're saying, I wouldn't build so-called a preset sequence, but I would build an adaptive sequence. When the next input to be applied will be, you know, like kind of applied in an intelligent way, depending on the output that was produced. So I'm going to do it in an adaptive step. And there are adaptive testing strategies, of course. So this is not a possibility. For example, for such an FSM, we can see if probably we cannot build a single DS, okay? But we can build, instead of preset one, we can build somehow a tree-like structure, which usually we refer to it as a test case, to actually still be able to conclude about necessary initial states and distinguishing the states between the implementation and specification, but in an adaptive way. So for instance, for this machine, you can see this is a test case. What's the difference is that now it's a tree-like structure. I don't know in which state I am, 1, 2, 3, 4. If I apply I1 and I observe O2, I can be at state 2 or 3 only. Otherwise, if I observe O2, it's 3 or 4. And then it also affects my choice. Either it's this one and I apply I1 next, or I apply I2 next. So I do it adaptively, and I have to store the whole tree or all the input-output sequences, because previously we were talking only about the input sequences, but now those are input-output sequences. And this is one of the beautiful possibilities, which I also wanted to show you how to reduce the corresponding test lengths. There are methods how to build it. We will not stop on it, okay? We will only say that in this case, instead of appending the distinguishing sequence, you can append a distinguishing test case. And probably it will help you size-wise, because the height of a test case, which is distinguishing, is polynomial against the exponential length of a distinguishing sequence. But you know, you need to build this test case and you need to store it somewhere. And you need to allow yourself, when you actually test your system, to be able to test it in an adaptive way, not preset. There are other things that we did not touch. And I think that I would rather move to the conclusions, taking into account the time constraints. Because in fact, what you can do is that you can also test non-initialized machines, which means that you can say, but there were, because you remember I told you, there are many, many strong assumptions, okay? And what we are working on is taking away these kind of restrictions, right? So you can say, I want to take away also the restriction of the fact that the machine should be initialized. Well, you can do it. And the techniques, they will be similar to those for the derivation of a distinguishing sequence. we did not touch at all other things, more complex specifications. When, for example, you can have predicates, which they were partially discussed in the talk of yesterday, when you can have, for instance, timeouts, when you can have time constraints, time guards, when in fact it's not only one machine, but it's a composition of the machines, you know. Or when your specification is located in the context of another machine, and you need to translate your test suite later on through a context. All these things, they are exactly, you know, how you say, filling themselves with new results in the corresponding area, but still there is a lot to do. Again, complexity-wise, fault coverage-wise, yeah, and many questions, they are still, people, they remain uncertain, because even the definitions of some objects, such as distinguishing sequences, for instance, for non-classical state models, it's a serious question, and people, they like to fight about it, let's say. So that's why it's also an ongoing area of research that I'm actually challenging you to give a look to, and maybe if interested, to join. That's the story. So I guess that on that one, well, you will find the slides, I assume, and things like that, so you will get some references, obviously. I'll probably conclude, because it's 1:30, and because if I'm not mistaken, there is a small break, and then it comes the talk of Jorge, right?